Okay, in this example, it says we have 50 mils of water. So we're going to go to our picture it. We have a beaker containing 50 mils of 100 degrees Celsius water. And then we have a larger bucket that has 10,000 mils of water, and it is at 20 degrees Celsius. Now you should know that when you take this larger one and you pour it into the smaller one, the temperature is going to be somewhere in the middle. Now it's going to be closer to the 20 degrees Celsius just because it has much more mass. So that kind of gives us a starting point for what we're looking for. Now the given information that we kind of have to split it up into two things. So we know the first beaker, I'm going to call that Q1. I'm going to call the other one Q2. Okay, I'm going to go ahead and separate them in terms of color as well. So for the first beaker, the one that's hot, I'm going to go ahead and say, all right, the mass is 50 grams. You may be saying, well, how did you get grams? Remember, the density of water is such that 1 gram of water has a mass of, or has a volume of 1 mil. So the density of water is always 1. So because of that, you can say that 1 mil is 1 gram, or 50 mils is 50 grams. You can say that the initial temperature of the object is 100 degrees Celsius. And then you can also say that the specific heat of water is 4,184. Okay, for the next one, I'm going to switch to blue because it's the cooler one. And what we can say is you have the mass is 10,000 grams. You can say that the initial temperature is 20 degrees Celsius, but it has the same specific heat capacity of 4,184, and that would be in joules per kilogram Kelvin. Okay, so what we were trying to find in this particular case is we are trying to solve for the final temperature. Remember, when you mix these two, they're going to equilibrate, and you're going to get one final temperature. So the principle that's involved here, really what we're talking about is we're talking about conservation of energy. The law of conservation of energy. The heat of one thing has to equal the heat gained by another. Okay, in other words, if you look at it in terms of a formula, the heat that is lost by the hot object, let's go ahead and keep it straight here. The heat that is lost by the hot side is going to equal the heat that is gained by the cold side. Remember that the formula for Q is Q equals Cm delta T. So now we can take a look at our solution. So how are we going to solve this? And what we're going to do is we're actually going to start to plug in our numbers. We can say, all right, if you have negative Q equal positive Q, you can also say negative Cm delta T equals positive Cm delta T. Remember, keep your sides straight. You have the hot side on the left, you have the cold side on the right. So now what you can say is you can say, okay, the specific heat is the same on both sides, so it cancels out. Now you can plug in your numbers, and you get negative 50 TF minus 100 equals equals 10,000 times TF minus 20. So now what do? Now what we're going to do is we're going to distribute. And when we distribute, what we're going to get is minus 50 TF plus 5,000, because we have to distribute the negative with both of those, equals 10,000 TF minus 20,000. Now you combine like terms. So I'm going to add 50 TF to both sides, and I'm going to subtract 5,000 from both sides. When I do that, what I'm left with is I get 10,050 TF equals 205,000, and now I can divide both sides by 10,500. And when I do that, I get my final temperature. The final temperature is 20.4 degrees Celsius. So now we look and we say, does our answer match what we were trying to find? Well, yeah, we were trying to find the final temperature, and we in fact found the final temperature. So we can check off this last box, and then we can also say, does it make sense with what our answer originally said? We said we would expect it to be closer to the 20